Chairman, Convent Technology. So I would request Professor S.P. Shah sir, please come on dais. I would request Dr. A.K. Chatterjee sir, please come on dais. To chair the session, I would request Dr. Manu Santanam sir, Professor IIT Madras, please come on dais. And to represent NCCBM, I would request Shri P.M. Oza sir to come on dais. I request Shri P.M. Oza sir, please present a bouquet to our speakers and chairman of the session. Shri P.M. Oza sir. Now I request Shri P.M. Oza sir, please introduce the chairman of this session, Dr. Manu Santanam sir. Although he is very well-known face, but it's still our duty to introduce him and take this session forward. Thank you, sir.
Thank you, Kapil. So we have two eminent speakers. So, and session chairman is Professor Manu Santanam. So he is a bachelor degree in civil engineering from IIT Madras and master's and PhD from Purdue University, USA. And he is a renowned concrete technologist of the country and a renowned concrete technologist overall at the world level also. So he is outstanding concrete technologist from Indian Concrete Institute. He got award in 2018 and Corps of Engineers Prize from Institution of Engineers in 2011. Then Professor P. Ramakrishna Award for outstanding young researchers in concrete technology and many more awards. And he has overall 17 international journal publications, 30 plus national journal publications, and more than 70 for conference papers. His research area is cement chemistry, multi-scale characterization of concrete, non-destructive testing, assessment of deterioration mechanism in concrete, machinery structure, 3D printing, concrete durability, use of supplementary cementitious material, and he is immensely contributing in formulation of Indian standards and Bureau of Indian standards in the field of concrete technology. So with this introduction of our chairman, I hand over the session to the chairman to conduct the sessions with two eminent speakers. Sir.
Thank you, Dr. Oza. It's indeed a pleasure to chair this session which has two very well-known stalwarts in the concrete industry. I don't think there will be anybody in the audience who does not know both of them, but it's my duty as chairman of this session to introduce today's speakers. We have with us, of course, Professor Shah and Dr. A.K. Chatterjee will be sharing their experiences and enlightening the audience with their ideas and concepts as to how we should move forward in the future. So, to begin with, we'll have Professor S.P. Shah, who is the Presidential Distinguished Professor at the University of Texas in Arlington, in the USA, and also he is a Professor Emeritus at Northwestern University in the US, And I'm also very happy to add that he's also a distinguished professor at IIT Madras, from where I also come. Professor Shah is a member of the National Academy of Inventors, National Academy of Engineering, Academy of Athens, Chinese Academy of Engineering, Indian Academy of Engineering, European Academy of Engineering, and Russian Academy of Engineering. He is the former director of the NSF-funded Science and Technology Center on Advanced Cement-Based Materials at Northwestern University, which led to a lot of groundbreaking research in the field of cementitious materials and concrete. He is responsible for developing a lot of different types of high-performance concrete, fiber-reinforced concrete, self-consolidated concrete, shrinkage-reducing admixtures, carbon nanotube reinforced cement-based composites, and extrusion processing of concrete. He has made unique, original, and extensive contributions to better understand and define properties of cement-based materials and developing new advanced materials, which has become a world standard in these fields. I also wanted to add that to all youngsters and up-and-coming researchers in concrete technology, he has always offered support and guidance, and he is always willing to listen to them and promote new ideas and new research in whichever corner of the world people are from. And he always makes it a point to engage with youngsters. So, Professor Shah, we'll have 40 minutes for this for the talk, followed by 5 minutes of questions and answers.
Good afternoon. It is my distinct pleasure to be here for this 18th conference sponsored by NCB. And I have probably a unique, or one of the unique experience that I knew Dr. Vishwa Salaya. I met him during the first, he was the first director, and I also met Malik. He was the second director. And I'm especially delighted to be here because L.P. Singh, who is the General Secretary of NCB, he spent some time with me at Northwestern University. And you know, one of the pleasures of teaching is that you learn from the students. So LP told me that before you start your talk, you must tell a joke. So I'm not good, but I remember one joke that what would be the best thing in the world for a person? Well, there's an American income, a house in England, Italian food, and cement in India. What would you tell? What would be the worst thing? Well, worst thing would be an American wife, British food, Italian management, and Indian bureaucracy. Now, I must add that's a joke because my wife, who is excellent, is also American. So I want to talk about some work that has been doing primarily for my group and others on what I call carbon conscious concrete. And as we know, and as was presented in the panel session and during the rest of this conference, there are several ways we can achieve this goal, let's say in 2017. Let me see, does this work? No? What happened? So what I want to do is how nanotechnology can help achieve this goal. So nanotechnology can enhance properties, obviously we've seen mechanical properties, durability, that would enhance the lifetime of structure, which will obviously be a right way for carbon footprint, and also some of the aspects I won't talk about it. Nanotechnology can manipulate thermoelectric properties which could be used for insulating buildings. What I would like to emphasize more is that how nanotechnology can help accelerate carbon capture, utilization, and storage. We also talk about how nanotechnology can enable recycling of waste materials, and finally, how we can develop carbon negative supplementary cementitious materials. So I'm going to start with nanosilica. Obviously, nanosilica is used quite a bit. I know that LP has one of the pioneers working in nanosilica. So I want to show some examples. For example, I want to start with coating. You know that the damage of the structures that start at the surface. So if you can prevent aggressive chemical ions and water and other things getting into the surface, then we can substantially extend the life. And there are essentially three types of coating: epoxy coating, silane, or which I call hydrophobic, and a mineral impregnation. I want to concentrate on mineral impregnation. And what I want to do is that work that has been done quite a bit with historic stone structures, solidifying them with tails. Tails is like the water, so it can go deep into concrete surface, and reacting with calcium hydroxide, it develops nanosilica and then of course pozzolanic material. As an illustration, I have plotted how much a surface can absorb water, and you can see the top one is controlled, while bottom one is the surface coated with tails, which is essentially nanosilica. Tails goes deeper on the surface, few millimeters than nanosilica. So, I don't know why this doesn't work. Okay. However, if you look at compare tails, coated surface, or I put nano sodium silicate or water glass, compared to control, it obviously absorbs less water, but not compared to silane. At least initially, silane, because of hydrophobicity, is much more, let's say, resistant to water. So what we did in conjunction with my former students and my colleague at Jinan University, so we developed what is called core shell nanoparticles. So it is core of silane surrounded by nanosilica. So you have both hydrophobicity as well as pozzolanic material. And I won't go into detail about how it's manufactured using soil gel process, but if you look at the results, the top is controlled, next to it is tails coated, next to it is silane. The least water absorptive material is this core shell, silane and nanosilica. So that's really one way what nanosilica can really provide, essentially very impermeable surface. Another example where nanosilica can help is in recycled aggregate. We know that we would like to use recycled aggregate into making new concrete. The problem is that there is an interface surrounding the natural aggregate which is very thin and porous, and that produces, among other things, when you use that in making new concrete, durability and strength issues. So the people have been working on it, for example, carbonation, which I will talk later on, or removing this with heat treatment, or people also use mechanical grinding, and that's also one. But today I want to talk about nanosilica. So if you look at here, how much water can be absorbed? So the black one is natural aggregate, the red or maroon, substantially the recycled aggregate without any treatment. And if you look at the blue, adding, that is, you immerse it in the water containing nanosilica or chaos, then you get substantially less absorption. So it's another role of nanosilica. Now, I want to talk about, and actually rest of my talk essentially is going to talk about how nanoparticles can help enhance carbon capture and utilization. And we know why we want to do it. I think that earlier several people mentioned that of course we have low carbon concrete, which India has done quite well, but a step further is the carbon capture and utilization. And that's what I want to see how nanotechnology can help. So if you look at the carbon sequestration, you can do dry curing, which is for, let's say, for precast product, and for in-place concrete, one can do wet curing. Now, many of these supplementary materials that we talk about for low carbon concrete has lower in calcium. So they would not be as effective as Portland cement in absorbing CO2 for carbonation. So what I'm going to show you is that addition of small amount of nanosilica in low carbon cementitious material, such as LC3 and others, you can enhance carbonation. But before that, I also want to point out that when you carbonate concrete, dry or wet, normally we talk about calcium carbonate as calcite. But in fact, there are 4 polymorphs of calcium carbonate. And it turns out that the most stable one is calcite. But if we can find to produce more aragonite, then material, that carbonate provides more strength and durability to result in concrete. So if you keep that in mind, in fact, right now, there is a company in the US which is selling aragonite as a supplementary cementitious material. So what we did, this is again the work I did with my former students at Hanan University. So they developed in the lab a low carbon cement composition, and you can see the comparison with clinker and the so-called low calcium CO2. And then they carbonated it with addition of nanosilica. So if you look at the graph on your left, the extreme left is this low carbon cement material carbonation and amount of carbonate, especially amount of aragonite. Then look at when you have added 0.06% of nanosilica, I mark that with a red line. You can see amount of aragonite has substantially increased. So not only you have carbonated, but you have changed the morphology. And as a consequence, if you look to your right, the compressive strength, so you can see that after carbonation, when you have small amount of nanosilica, compressive strength, in fact, has gone up. So that's about nanosilica. Let me talk a bit about nanotitanium dioxide. I think many of you have heard about so-called self-cleaning surface, where we have nanotitanium, so because of photocatalytic activity, it converts the harmful gas into not so harmful, and then because of hydrophobicity, they wash out. And here, for example, a famous example in Rome. Now, they added it to the entire concrete during mix. But of course, nanotitanium is very expensive. So why not just add as a coating, spray? The problem is that when you have cement or mortar coating with nanotitanium, it doesn't bond well with the substrate. So again, I wanted to mention that develop a core cell of nanosilica and titanium dioxide. So when you put that surface, because of nanosilica pozoronic activity, it bonds well, and then titanium dioxide does photocatalytic activity. There are nanotitanium dioxide have other uses too, and there is a lot of work being done at Purdue University on using nanotitanium dioxide. What they found out that when you carbonate concrete sample, So addition of small amount of 1% in titanium dioxide has increased the uptake. And why is it? Well, they speculated that adding, and I will come back to it, adding nano titanium dioxide decreases the size of calcium hydroxide crystal. And if that is true, then we have a large surface area. They also speculated that although you decrease the pore size, you increase the surface of the pore, and so you get more CO2. So when I was thinking about, and then again here you can see what is the optimum for carbonation of nano, with 0.5%. So we had done some work earlier with, before I go to that. Now, what we have been talking about with the highway department, especially the Indiana DOT, is that if you have concrete pavement or even asphaltic pavement and have a thin coating of nano titanium dioxide, then as the car go by, because of photocatalytic activity, they will make, but will absorb CO2. So this is what more an idea than a reality, but it seems like a good way, especially in the busy cities and parking lot where you have a lot of noxious gases and CO2 have a thin coating of containing nanosilica. So this is the idea, and I won't go into the detail now. But what I want to talk about now is nano-graphene-based material. And when we talk with Purdue people and say that one of the possibility of enhanced absorption or sequestration of CO2 is decreasing size of calcium hydroxide crystal. And we had observed that when we add very small amount of carbon-based material such as carbon nanotube or graphene oxide, and here I'm going to talk about, it also reduces the size of calcium hydroxide. And it does other things in altering CSH. We won't talk about it. So we said, okay, let's see whether GO or graphene oxide also enhances carbon capture. So we did some work, and clearly when you have nanoparticles, especially nano graphene-based material, they have a large surface area, so your dispersion is a key issue, and we have developed it. So using our process, we disperse small amount of GO and then carbonate it. And when you look at the results, some very interesting results. So here to your right is how much a specimen of cement paste absorbs CO2 during carbonation, and how much small amount, we're talking about 0.05% of weight in GO, which cost-wise was less than superplasticizer, increases CO2 uptake by 30%. And one reason, as I already mentioned, reduction in calcium hydroxide crystal. And especially for GO, if you can look from the zeta potential, you have this calcium ion attached to that surface, and so it enhances CO2. And what is also interesting, that addition of this small amount of graphene oxide also increases compressive strength. So here I've plotted with and without both uncarbonated and carbonated, and you can see you can substantially increase in compressive strength. At the same time, substantial increase in CO2 sequestration. I now also talk about nanocellulose fiber. There is a lot of interest now in natural fiber. It makes sense because currently we are using man-made fibers such as steel or polypropylene, PVA, and can be substituted obviously some specific application by natural fiber. So we did, along with my colleague Varda Ashraf, some work in see what can we do to manipulate So what here I've shown, oh, I showed wrong way, huh? Why isn't it going the right way, huh? Welcome, what am I doing wrong? Nanofiber was there, and the next one. Okay, so this is some work of how we can alter the morphology of calcium carbonate. And so I want to show results with two things. One is a biopolymer called polydopamine, and other one is cellulose fiber. So what is plotted here is on the y-axis relative amount of unstable or metastable calcium carbonate, primarily aragonite, and with control, the next to it is 0.1% of polydopamine, and next to it 0.1% cellulose nanofiber. So adding this and carbonation, we have increased the amount of CO2 sequestration. And as a result, not surprisingly, we have increased the compressive strength by, in case of biopolymer, 36%, with not so much, and I will show you why, with cellulose nanofiber, 8%. So the idea is that, manipulating calcium carbonate has substantially, significantly beneficial result. So I also now want to continue with natural fibers such as cellulose, jute, tricycle. And we know that if they are untreated, and if you add that as a reinforcement in concrete, if you do not use the laying, then you have durability issues. Here, for example, we show the interface between untreated cellulose fiber and cement, and you can see big cavities. So for pre-card product, why not carbonate the cement, reinforcing cellulose fiber? And here are some results. So you can see, for example, to your left, in moisturing, we have a result for 3, 7, and 28 days. And you can see that untreated cellulose fiber at 28 days has a reduction in compressive strength. If you carbonate it, then you can see that because we are not only calcium hydroxide is gone, but we have calcium carbonate, enhance the interface. So 50% increase in flexural strength to your lab, and 36% increase in compressive strength. So we have sequestered CO2, we have used natural fibers, which is replacing man-made fibers, and increased mechanical and other properties. Now, I want to talk about a couple of items about how nanotechnology can help in producing what I call carbon-negative supplementary cementitious material. One example, is the recycle aggregate. We know that we have a large supply of recycle aggregate from construction debris, whether natural disaster or man-made demolition, and we want to use them to replace them in natural aggregate. This is especially true with sand, because there is really worldwide shortage on sand. So we are having some trouble with okay. So quite a bit of work done, some also commercially by C.S. Kuhn in Hong Kong in carbonating recycle aggregate. And you can see, as I mentioned, you have this thin layer surrounding the natural aggregate, and if you carbonate it, then obviously the calcium hydroxide is converted into calcium carbonate, and you have a very, almost like a natural aggregate of recycle. But what I want to draw your attention, I don't know why this is not moving, is the effect of the aggregate, recycled aggregate size after carbonation. And what, so with coarse carbonate it, you don't have not only have a calcium carbonate, but because the silica, amorphous silica is removed from CSA, so you have amorphous silica, which can be used as a supplementary cementitious material. So you are doing two things, replacing sand, absorbing calcium carbonate, and providing amorphous silica, which is a pozzolanic material. So that's quite interesting for the fine side. Is there some magic word I should say? So second example is when you have the trucks, ready-mix trucks come back, you wash it, and you have this wash water which contains cement. Normally, it's dumped. So instead, you take the wash water, remove the coarse aggregate, and then carbonate the slurry. When you carbonate the slurry, you find out that it acts as a pozzolanic material. For example, to the right I have shown compressive strength of control that is added, recycle aggregate slurry without carbonation, and recycle aggregate slurry with carbonation. And this is obviously done at the plant of Europe, and couple of the Japanese companies are doing it. So you have a recycled wash water and you made into SCM, supplementary cementitious, and you absorb CO2. So then, I missed one. One of my former students, Shioka, she is now in Columbia and working with the professor in chemical engineering, Elisa Park. They have developed a very interesting process called two-step. So you take a waste material, this is alkaline waste material, which moves waste material, or not only construction waste but applies to mineral waste. So two-step extraction process. First is the acidic, that is very low pH, and when you do that, produce as shown as supplementary cementitious material. The next step is that you increase the pH and then carbonate it. And what they have found out that process, they can produce individual morph of calcium carbonate. And as I've shown in the right side, what is the effect of each of the morph aragonite and bentonite on hydration and other properties. So I think that this is a very interesting process that you take waste material and develop into, absorb carbon dioxide and develop into supplementary material. So the last, we talked about that. Okay. The last one I want to talk about, very interesting aspect of addition of carbon nanotube. You know, we all often rightly concentrate on compressive strength and some applications natural strength. But it turns out that in some applications we want to increase modulus of elasticity of molecule. One example is obviously super tall building that was mentioned in one of the videos. And super tall buildings are possible because you can have concrete with high compressive strength. But they also need a high modulus because of the wind or the earthquake effect, and they would like to have double the modulus of concrete. Instead of, let's say, 30, they want a 60 GPa. So currently, way to do it is, we know the relation between modulus of elasticity and swell, which I have shown here to the right. So currently, the only way you can increase modulus is increase compressive strength. Increasing compressive strength means more cement and also material. So we found out that addition of 0.1% of multiple carbon nanotube increases the modulus that's shown here by the red dot at 40 megapascal. So you can get the same modulus at a lower compressive strength that has lower cement. And so this is one I'm going to conclude now and not talk about his remaining and stop for the questions.
Thank you very much, Professor Shah. I think you did what you always do. Present very new ideas and also germinate new seeds of thought in the mind of young researchers. I'm sure that I'm saying that you're always germinating new ideas in the minds of young researchers. Thank you so much for that. I'm sure that there'll be a few questions from the audience.
I have a nice presentation. I just have a question on cellulose fibers that you talked about. One is on the durability of cellulose fibers over a period of time, because they are natural fibers and they are prone to alkali attack. Number two, on the source of the cellulose fibers, whether it's wood, cellulose, or algae based. So these are the two. Stability of cellulose fibers over a period of time under the alkaline conditions. Second is the source of the cellulose fiber, whether it is wood, pulp, or algae based.
So, currently the way we do it is remove the lignin. And currently what the cellulose fibers on market are very stable because there is no lignin. Another way is without that treatment, you take cellulose fiber, add it in cement, and during curing use CO2 curing. So CO2 curing, and it's you don't have calcium hydroxide, is converted into calcium carbonate. And we have seen that the interface between fiber untreated is quite dense. So that's what happens. And then, so absorb CO2 and improve the durability of untreated natural fibers.
I think there was also a question on the source of the cellulose fibers. The source of the cellulose fibers. Yeah. Whether from the pulp or...
The one that we use came from paper industry. And actually that was waste cellulose fiber. But there are a whole bunch of other sources available. And
Yeah.
Shah, that last slide that you showed, you mentioned that the modulus of elasticity can be doubled without increasing strength, because increasing strength means more cement. But I couldn't quite follow how it can be done. How do you do it? How can you explain the last slide?
very good point. And you are of course very well-known structural engineer. So when I presented this result at ACI, the people who were designing the new Freedom Tower, they were very excited. They said, "Suru, can you supply me?" Because we were doing a high-rise and we work, even of course in the laboratory we produce a small amount, so scaling up. So what happens when we have 0.1% of carbon nanotube? So it improves, and I quickly went through this side, it improves the interface. As a result, it increases the modulus, but it doesn't go, it doesn't do much to compressive strength. So we have found another tool that when you use, except for graphene oxide, for different reasons, the graphene-based nanomaterial, there's a lot of things, but generally doesn't improve compressive strength. And as a result, that's one of the reasons it's not doing marketing-wise, because people look for compressive strength normally as a criteria for improvement. Graphene oxide is different for a variety of reasons.
There's a question.
Sir, you presented very interesting work on that core shell
Because if it doesn't break, then how the effect of silane or how the effect of titanium would be observed in cement?
This nice quote versus spherical shell is a cartoon presentation. If you look at TEM, then some part is covered and some is not, obviously. So that's only, so you get exposed to both of them. See, both atom or both silica, nanosilica and silane. And I have one TEM picture I didn't point it out. So it's not completely covered.
Silane will be in a liquid form and titanium will be in a powder form. Is it, am I right?
Silane was with nanosilica.
Yeah.
And both were in
But silica outside is now solid because it's a solid particle. So you mentioned that it is kind of, it is also reacting with the cement or something like that, that outside silica? Bentonite.
done when, and I can send you the publication that we have.
We'll take one last question. Excuse me.
First of all, I would like to say thanks, Professor, enlightening so many aspects of nanotechnology technology. I have two questions. Like as you have mentioned, the polymorphs of calcite, like calcite, aragonite, and hydrite. Aragonite is showing some SCM activities while being used in concrete, but chemically these are basically calcium carbonate. So how this is being reacting or activating the concrete while mixing with the concrete? And the next one is you have mentioned by addition of graphene, approximately 8% of size reduction is happening with crystalline calcium hydroxide. Is there any method to detect that, how much the size is getting reduced?
The aragonite doesn't really, have vibration, but because of its crystal structure, when you carbonate it, it will provide higher compressive strength and other properties compared to calcium, primarily the surface area. Similarly, if you, one of them is, the most unstable one, which are spherical particles with a lot of surface area, and that, and so that's how it happens. And I forgot the second question.
With respect to the graphene, reducing the crystalline size of calcium.
Oh yeah, that's a very good question, and I don't have the answer why addition of GO reduces the crystal size. One speculation is that because, as I show you, especially with graphene oxide, calcium ion are attached to the GO, and so maybe less calcium resolution and lower calcium hydroxide crystal, but I don't have a good answer. But we have seen with the XR diffraction that indeed calcium hydroxide size is different. Another thing also with both GO and carbon nanotube, similar to nanosilica that LP and other have found, it changes the CSH it polymerized more polymerized CS with addition of CNTN. So that makes it more stronger.
Thank you so much.
Thank you, Professor Shah. With that, we'll close the first lecture. Thank you so much. Once again, a big hand. Our next speaker also does not need any introduction. He's been at home here in this conference because he was also one of the founding members of